Okay, problem number 5. We're told that we have a coil and we have a wire carrying a current. I guess for the sake of the problem, it's we can just kind of like lay it across the diameter of the coil, right? So what we're asked to find is what is the net flux going through the coil after we lay the wire across the diameter of the coil. And so I've drawn it 3 different ways just so we can kind of get a good look at it. This is sort of like a laying down side view. This is a standing up side view, which is pretty much the same. And this is a top view. And so from the top view, we can kind of see if this current is going this way, we're going to have a B field that goes around this way. So it's going to go into the page here, but it's going to come back around out of the page here. And it's going to keep doing that in all of the space, right, until it dissipates and disappears. And so what that means is that the magnetic field flux going in to the coil is the same as it is coming out of the coil and on this side, right? And so that's pretty much, we can say that the net flux is going to be, goes in minus out, and those are equal in magnitude, and so then we have no net flux. No net flux. There is flux on this side, and there is flux on this side, but the overall net flux from the wire through the coil is 0. Okay? And then we have another scenario where now we take the wire and we place it through the coil, and we're asked to find the net flux. Well, what we want to consider is that our formula for flux is magnetic field strength times the area times cosine of the angle between what it says in the book is between the plane of the area of the coil, so in other words, this plane here, and the current carrying wire. And so in this case, that's going to be 90 degrees. So it doesn't really matter what these values are, because if we cosine 90 degrees, it's going to equal 0. And so then, again, we have no net flux going through this coil. And I mean, that makes sense. If you look at this thing going this way is going to give us magnetic field going here, and this is parallel to the coil itself, so there's not really going to be much of anything going through the coil. So that is that problem. Next problem, we're given another coil. We're given a magnetic field with a flux going through the coil, so this will have a net flux. We're told that the net flux is 2.7 Weber. We're told that the field strength is 0.3 Tesla, and we're asked to find R. Okay, so pretty much this is just plug in to the formula. We know that the field strength is 0.3 Tesla. We know that the angle between them is going to be 0 degrees. Again, because the plane of this area is going to be parallel to some current producing wire that's making the B field come this way, right? So that's cosine of 0. Okay, and that's going to be equal to 2.7 Weber, right? So then we just, oops, this is area, not R, my bad. So then we solve for R. Well, area is equal to pi r squared, so we can plug that in. So let's take 2.7, let's rearrange a little bit, 2.7 over 3.3 Tesla over pi, all under a square root. That will give us R. Right? And then we plug it in to the calculator, 1.69 meters. That's what I got. Okay. Next problem. We're given, this is number 10. We're given a coil of wire, and it's sitting in a B field, right? This is a magnetic field going into the page. We are told that the radius is 0.12 meters. We're told that the field strength is 0.15 Tesla. Then we're told we grab points A and B and we stretch them apart, right? We pull them until the coil flattens out, and then there is no flux going through the coil at all. So we're given a change in the flux, right? And we're also told that this happens over a period of 0.2 seconds. So let's look at our formula for, let's just move that, right? So our EMF is going to be change in the flux over a change in time. And since the plane of the coil doesn't actually change, the shape does, but it remains within the same plane, so that doesn't change. So the angle between these things doesn't change. So then we're just going to leave that at cosine 0 degrees times the field strength times the area times the change in the area, because we're actually changing the shape of the coil itself, right? And then we are asked to find the EMF. So let's plug all of this in. We have 0.15 Tesla. This does not change. Then we have change in the area. We have pi. It's going to be pi r squared, right? But r squared in this case is going to be 0.12 meters squared minus 0, because the area of inside the coil effectively becomes 0 once it's squished, all over a period of 0.2 seconds. Because delta t is 0.2 minus 0 seconds. So that's pretty much it. And we just plug it in and we get a value of 3.39 times 10 to the negative 2 volts. Right? And that gives us about 34 millivolts. Okay? We'll just go ahead and do the next one because these are all pretty short problems. The next problem, somewhere down here. Okay, we're given that we have a charging station, and there's a coil inside this charging station. And so what happens is we vary the B field. We're told the max B field is 10 to the negative 3 Tesla. And we want to vary this so that it creates a flux and then creates an EMF that charges the battery. Okay, so pretty much we're asked to find how much time does it take to go from the maximum to 0 for the B field. And we're given an EMF. Let's remember that this is the change in the flux over the change in the time, which we're actually asked to find the change in the time. So let's just rearrange this right away. Change in the flux over the EMF is equal to the change in time. And that's going to equal, so the change in the flux is going to equal, let's do this. Let's go. The area of the coil does not change, right? The angle between the plane of the coil and the current carrying wire does not change. So those are the same. So times cosine of the angle, these do not change. The B field is what changes over our EMF, right? So we're actually told the area, that's 3 times 10 to the negative 4 square meters. We're actually told the EMF, that's 5 volts. And now we're given, let's see, we're told that the maximum B field is 10 to the negative 3 Tesla, and then we want to go down to 0 Tesla. right? Final minus initial, right? So this is B final minus B initial. So this is what I'm using for that. Let's move this so it doesn't look like it's part of the equation. I was just demonstrating what we're doing. Okay. Okay, I believe we just plug this stuff in now. Just double checking, make sure I got everything. Actually, it's important that we stop for a second and recognize that the EMF is actually, this is not explicitly the correct formula. It is negative times the number of turns times the change in flux over the change in the time. We are actually given a number for the number of coils that we have within this charging station. So we have 15 turns around the coil. Okay, so that's important. We have to use that. We're also given that, so I had this backwards, the final is 0, and the initial is what we're given. Because we start out at max, and we go to 0. Okay? And then, so we have to multiply 15 turns, and a -1, and then a -1, and 15 turns. So let me just rewrite this real quick, more explicitly. So I rearranged, right, so that the change in the flux, sorry, the change in the time is equal to the change in the flux over the EMF. Okay, so that's area times cosine of the angle is 0 in this case. We have a negative n times A, and then 0 minus 10 to the -3 Tesla over 5 volts. Okay, so that's what we plug in. So this is, we're given this value and we're given this value. This is 15, and so I wrote that over here. 15 turns, and 3 times 10 to the -4. So 15, 3 times 10 to the -4, -10 to the -3, over 5. This gives us a value of, let me just double check this, 9 times 10 to the -7 seconds, or 0.9 microseconds is how long it takes to vary the B field from its max to its minimum, which is 0. Okay.